So first of all, we're going to look at probability distributions. Okay. So what is a probability distribution? What it does is it assigns a numerical value to every outcome in our sample space. It's probability. Now, outcomes. We could have a numeric outcome. So in other words, we come up with a value, a number. Every element in the sample space would have a numeric value. So the example I put there is rolling a dice. You get a 1, a 2, a 3, a 4, a 5, or a 6. But we also have what's called categorical ones. So the elements aren't actually numeric, but they could be a description, it could be a word, it could be... So the example I've given there are blood types. You have, what do you have, A positive, O, all those sorts of things. So they're not actually numerical values. So a random variable is actually a function. Okay? And the value of that is determined by the probability. Some notation rules here. So our random variables we usually use an uppercase letter for, or capital letter if you want to give it a fancy name. Their values then are represented by the corresponding lowercase letter. Now, you might have heard about, when you did stats previously, you might have heard about continuous distributions and discrete distributions. So random variables, really we're talking about the distribution. So it could be continuous if the range of this function, so all the output, is an infinite set of real numbers. And so you can't have discrete values, I guess is what we're saying here. As opposed to, well, hence the name discrete, where the range is what we call countable. See, with a continuous one, it would be impossible to count all the possible values in a sample space, because you can keep dividing. You might be talking about, height. Now, theoretically, you can keep dividing the units into smaller and smaller and smaller units. So you'd end up with an infinite number of possibilities. Whereas a discrete one, we're saying if it is countable. Interesting thing there, by the way. It is possible for something to be infinitely countable. I know that sounds weird, but they're still discrete values. So the example there I've got is the number of times a dice is rolled before a 6 occurs. Now, theoretically, you might never roll a 6. So it is theoretically possible to have an infinite number of values there. But we still call that countable because the numbers are going to be counting numbers, be once or twice or 3 times or so on. So that's a really strange one where you've got an infinite number of values, but we still call it a discrete distribution. Okay, let's have a look at an example then. So this year what we're interested in, we're going to be looking at discrete distributions. In year 12 we look at continuous distributions. So we take it a step further. So discrete ones. So good old tossing a coin. We're going to toss it 3 times. My random variable, my function x, I'm going to define it as the number of heads thrown. So the number of heads thrown. So my sample space would consist of all these. I could get head, 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 tail, head, tail, head, tail, head, head, tail, tail, head, tail, head, tail, head, tail, tail, or tail, tail, tail. Okay, so that would be my sample space there of all the possible outcomes I could get. But the sample space of the random variable are not those, because remember, we want the outcomes, we want the value. So 3 heads are thrown, 2 heads are thrown. Remember, x is not the outcomes. We've defined x to be the number of heads thrown. So each one of those would convert to a number. 3, 2, 2, 2, 1, 1, 1, and 0. And I could draw it up in a table. Now in stats we called it a frequency distribution table, but now we're calling it a probability distribution table, because instead of writing the frequencies down, 1, 3, 3, 1, I'm writing the probabilities down. 1 in 8, 3 in 8, 3 in 8, 1 in 8. That's really all the difference. You'll notice the notation here. Probability that capital X, that was the function, is equal to little x, that was the outcome. So probability that it was equal to 0 would be 1 in 8. Probability that x was equal to 1 would be 3 in 8, and so on. Okay, so that's our probability distribution. Of course, we could graph it. Again, in stats, you drew, what do we call them in stats? Frequency distribution polygons and things like that. Basically, it's a graph. I've done it as a plot with a dot plot. But again, you can see the axis here is probability x equals x, and then there's our possible outcomes there, 0, 1, 2, 3. And not a very interesting graph, but there it is. That would be the graph of the probability distribution. So some properties of this idea, the probability of x equals x. Okay, probability of x equals x must be greater than or equal to 0. The sum of them all must be 1. Because what we're saying is we're adding up all the probabilities, and we know all the probabilities add up to be 1. Now, if that probability is the same for all values, in our example it's not, but if it was the same, we would call that distribution uniform. It also means we're talking about equally likely events, if we gave it some probability terminology there. So if every event came up with the same probability, we'd have a uniform. And so the graph, again, would be rather boring. It'd just be a straight line. Okay, so that's just an introduction to our idea of probability distributions. And so there's 16 questions there to do.